Is everyone? Oh,
Yeah, are you ready?
Oh yeah, I'm ready. Sorry for you are ready. Okay.
I think everybody is ready. So good morning, everyone. Welcome to the second day of mini courses. Let's start today's lecture. So we're happy to have Professor Shigeru Mukai again for the second lecture of birational automorphism of holomorphic Sym-plectic manifolds. Yeah, please.
Thank you. Okay. So yesterday I gave two examples. So with Picard number 2, maybe the simplest. Of course, you can consider Picard number 1 case, but in that case, automorphism group is always finite, and birational auto is always finite. So the interesting thing in view of automorphism starts from Picard number 2. And in the first section, I consider Hilbert square of K3 surface, and it's another extremal ray. What is their type? And in some case, you get S2, non-Hilbert square appears as deformation. The most interesting case, you get singular Debaré-Boisson variety fourfold with which is singular along a surface. And in section 2, I gave another example, which is non-Hilbert square. This is found by Hassett. And in this case, automorphism group, birational automorphism group is Z, and this is in this case also finite. So there are two distinctions. Okay. That now I want to proceed to the case. Sorry, I cannot understand the Chinese. May I neglect? Okay. But recall the following fact. So by Torelli's theorem, automorphism group of K3 surface, so this is K3, classical case, is up to finite groups, just orthogonal group divided by group generated by -2 reflections. So -2 reflection is x goes to x plus xaa square. This is R. And geometrically, this -2 reflection, -2 class is -2 P1 CS. And this is P1, and C square is -2. And for K32, Hilbert square, almost the same. In higher dimension, we get class with, so for K3 N case, we need class with this one, etc. Not only this one, but you need some other class also. But for n equal to, this is -2. So I'm sorry, birational. maybe let's yeah, Birational is again or e to x. So this is K32. The deformation type is K32. And in this case, you can consider also PQX as a lattice by Beauvais form, Beauvais quadratic form. And the same as above, this one, by this reason. But there's a difference. I already explained about the different new ingredient about the flop already. So the other point to care is the what is -2 object. So -2 object. There are two kinds. Numerically same, but there are two kinds. So in both cases, Q effective divisor and sum divisor is contracted by extremal contraction. And this is divisorial. And the divisor D so divisor is contracted to a K3 surface, a K3. Not usual, not necessarily the K3 which we start. Sometimes another K3. And this is a P1 bundle. And fiber is -2 P1. So in this respect, this is a very natural generalization of K3 case. And this is contained, this class is contained in extremally R. And the two difference becomes so -2 object, or maybe class is a better word, class alpha. So the divisor class. So first case is honest case. So, and this is, they are distinguished by divisibility. Divisibility of alpha is 1 here, 2 here. So divisibility is of alpha is greatest common divisors of all alpha beta intersection number, where beta runs all H2 of X. There are two cases, and in this honest case, alpha D is contained this -2 class. And no honest case, alpha itself has no effective member, but twice of alpha contains unique member D, and this D is contracted to S prime. And in this case, this X bar is a symmetric product of this K3 surface S dash, and this S dash is this S dash is diagonal. Yes. So this is a picture about, and we have a flop, but the flop doesn't affect for birationals. When you consider automorphism, then you consider flop also, and you consider NEFCON also. But this is another subject. In this birational setting, we only have to consider two types, two divisorial. So yeah. So this is we are studying movable. Yes. Yes. Oh yeah. He was. Yeah. Thank you. And yes, Hilbert square. So it's plan. I learned this from Hassett-Chinkel's some paper. I don't know who first proved it. This is a classification of extremal ray of holomorphic sym-plectic manifold. So using these generalities, I want to study birational automorphism group of Hilbert square of Inoue, as I wrote in my abstract. And in this case, this one has Picard number 19. I postpone the answer, final answer. So please wait. Be patient. What is this group? Yes. Thank you. So thank you. So this one. Yeah. This is. Yeah. Oh no. Okay. Thank you. Just a moment. This is the whole thing. So okay. This one has yeah. So this itself has become number 18. Yeah. Thank you. And Inoue surface was found or constructed in 90s. And this is two parameter families of quartic surface. And first, I consider its equation, y squared zt minus 4x cubed z plus 3a. So this is one parameter, ax zt squared. This is not so important, but let me write because I prepared. That's the only reason. And z square t square plus t fourth plus bx t cube in P3 with coordinate x, y, z, t. So first observation is there's two lines. So L1, which is z equal t equal 0. Am I sure? Z t p t, okay, yes. And L2, x equal t equal 0. Yeah. And they intersect. Let me. L1, L2. This is about information on two lines. And also this has two singularities. So one is 0, 1, 0, 0. This is nothing but L1 intersection of L1 and L2. And another point is 0, 0, 1, 0, which is in L2. So maybe better. I don't know. So this is 0, each 0, 0. And this L2, on L2, you have another singular point, 0, 0, 1, 0. And what type of singularities? And the answer is here, singularity is type A11. Here, singularity is 6. And so take a minimal resolution. Then you get the configuration. So first is A11. So chain configuration of -2p1. And on the strict transform of L1 attached to the third P1. I never computed, so I'm just following the paper. And something wrong. Yeah, okay, L1. And L2, is it correct? A11 is here. Yeah. So we have almost here. And L2 attaches the final -2p1. And on L2, you have E6 singularity. So famous Kleinian singularity or Duval singularity which has many names. Yes, one of famous singularities. Okay, and what is this K3 surface? I think Inose didn't find from this equation. He of course know the source of this surface, and the source of this surface comes from the following view. So you get 2 E8 children in this diagram. That's more essential in understanding of this, and also his purpose. In fact, I don't know why Inose-san consider write this equation, but yeah, that's another one. That is one. And here we have. So E8 children. And if you have E8 children, then consider the divisor with this one, 2, 4, 6. This is well known. If you take a linear combination of this -2p1s with coefficient these numbers, this is the level of affine E8 children diagram, then you get, so this is D, phi D, you get elliptic fibrillation. And this D goes to 0. And this D prime, so maybe change the color. Same way, 6, 4, 2, 3, 5, 4, 3, 2, 1, you get D prime. And D prime goes to infinity. So this surface is nothing but elliptic K3 with 2 E8 children fibrillation. But by some reason, he embedded into P3 by Neff divisor with H square of degree 4, self-intersecting number 4. Yes. Birational, because I'm sorry, birational element. Yeah, as I said, this is yeah. So just this A11 diagram, sub-diagram, and E6 sub-diagram is contracted. Okay, so the main motivation of his and his collaborator, Professor Shioda, was the following theorem. Following theorem. Shioda. This appeared in the same year. So their main interest is K3 surface with Picard number 20. So this is maximal Picard number when you consider over complex number. Then, so K3, their theorem is S is isomorphic to SAB for suitable parameter A and B. And in particular, S has elliptic fibrillation with 2E8 chip. And the reason why I mentioned this theorem is the corollary of this theorem. As a corollary of this theorem, they obtained maybe the first result in finite or infiniteness of K3, automorphism of K3. So when maximal Picard number, automorphism is always infinite. Maybe all that's a theorem about automorphism group in view of finite or infiniteness. The proof is not so difficult if one knows Shioda-Tate formula. So rank of model Bay group of this F is Picard number from -2 minus contribution of singular fibers or reducible singular fibers. So consider number of irreducible components of F minus X and subtract -1. So this is effect of singular fibers.
Yeah, so this section.
Yeah. But usually people say so. But if you replace Jacobian, this still holds for non-section case. Yeah. But of course, in this case, this has section. Sorry, thank you. I sometimes forget this one. Yes. Where? So this is section. Yes, thank you. So we answered in two ways. Yes, to your answer to your question. Where? So yeah, with two identified section and a section. Yes. Yeah. Mm-hmm. Oh yeah, yeah. Thank you. Yes. Yeah. So when this has no section, you have to explain. You just replace this by Jacobian fibrillation. Yeah. So apply Shioda Tate formula to this F. Then you get, so in this case, so this is a general formula. And in this case, we have, so Picard number is 20 and -2. And we know already there are two E8 Chulda. So E8 Chulda has 9 irreducible component. So -1, 8, -8, and something. And this part is already 2. So generally, one expects that this has a positive rank. So model Bayes rank is 2, except for 2 cases. So first case is SP1 has a fiber of type A2 or A2 Chulda, which means I think in Kodaira notation I3 and or in Kodaira notation, so this one, I forgot the name. This is 3 or 2, I forgot. Yeah. And second case is has a fibrillation, two fibers of type A1 Chulda. So A1 Chulda means this bygone or tangential bygone. Yeah, this is 1, 2. Yeah. So the former one is multiplicative type, and the latter one is additive ones. Anyhow, but they are A2 Chulda type and A1 Chulda type. And they find another elliptic fibrillation with positive model Bayes rank. Yeah, in their paper, but I omit that part. And so what? So in any case, translation by model Bayes group is a subgroup of automorphism group of K3 surface. And so this is infinite. So anyhow, if Picard number is 20, then they are always there is they always exist. I'm sorry. No. I'm sorry. Positive. So I'm sorry. Positive. Yes. Positive. Yes. So in generic case, this original F gives such vibration, and the space for these two special cases, try to find other ones. That's a good exercise, but let me omit. Anyhow, this is their proof. And remark, maybe okay. Remark is okay. So this is, as I said, so this is the first result. It's a first result on finiteness of automorphism group. Yes, the oldest result, I guess. And so I think the authors in this paper thought that what is a maximal Picard number among case-free surfaces with only finite automorphisms. And they could not give answer, but they write following remark. And so instead of this is very special, so this is two-dimensional family, but this rho equal 20 this is discrete. Infinite, but discrete. And oppositely, consider for so parameter very general. Then Picard number is 18. And in fact, its Picard group is generated by 19 minus 2p1 in the pi diagram. So let me call this pi diagram. Very long pi, but good approximation. And the duration is one. So these are almost basis, but only one relation. Only one relation. D linear equivalent to D prime. Almost basis. Yeah, one basis. Yes. And their remark is as follows. In Shioda Inose paper in 77 is so in this case, so when Picard number is 18, then automorphism group of SLB is finite. Okay. So they proved when Picard number is 20, always infinite, but there's an example with finite automorphism group with Picard number 18. And of course, question is how about 19? Okay. But before giving the answer, let me prove this remark. So in remark, it is written that by Bimberg, yes, by Bimberg result, yes, or more elementary, but anyhow Bimberg. Okay, so we have 19 P1s in pi diagram. And you just observe the following arithmetic. So pick S is U plus E8 plus E8. So this is negative definite part. So my notation is root diagram is root lattice is almost always negative definite, opposite sign I use. And this U is hyperbolic. You get the isomerism by part. Yeah, anyway, it's easy, yes. And consider element. Then if alpha satisfy 19 linear inequality, then alpha square is non-negative. This is the crucial computation. It's and this is also easy by Bimberg criterion, something like that. And this implies the following thing. So this means alpha such that alpha Ci is non-negative for all I. This is in peak X is the net cone of S. And this net cone is polyhedral, finite polyhedral net cone. So finite automorism. There's another method using by Nicourin, which uses the fact that this element, this lattice is two elementary, but moreover, in this case, unimodular. So you can construct a good involution. But let me omit the argument. I stick to this argument, or the original argument. And later, Nicourin classified all K3s with finite automorphism. This is equivalent to even integral lattice with fat O L W finite and rank L is at most 20. Yes, by Torelli. Geometric result, but and Nicourin himself used the geometric argument, but this is also arithmetical result. And in particular, he found one-dimensional family of SSAB. I forget how special, but yeah, with. And moreover, this is unique with. Fine. So by including the problem of classification is classified. So the problem implicitly mentioned or implicitly posed by Shioda Inose paper was solved by Nikuri. So one may be interested in how this generalized to higher dimensional symplectic manifolds. Yes. Yeah.
You have many
Yeah. Only one dimensional family. Yes. I can show them explicitly, but let me omit. Yes. 3, 4. No. His argument is very. I think the most interesting case is, as I mentioned, two elementary. So pick S, dual, pick S. This is two elementary. And in this case, very cleverly, Nikurin constructed involution, which acts +1 on pick X and -1 on transcendental part. And when you take quotient, this is in almost all cases, this is a rational surface. And the problem of finiteness becomes a problem of branch locus. Yeah. So, for example, if branch locus has a genus bigger than 2 or equal to, then this is finite automonism. This argument is very geometric. Yes. And this helps classification a lot. Yeah, a lot. But unfortunately, this technique doesn't seem to generalize in higher dimension. Yeah, that's the reason why I omit, but still worth to mention his inventive argument, geometric argument. So let's go to higher dimension. I only have partial result, but it may be worse. So what was the title? So what this title of this section is how the birational automonism group of Inose, Hilbert square of Inose. Yes. So I did a very long preparation, so you might forget what was the motivation. So where we are, let me see. I said this remark. This is very old. Oh yeah. It hides. Yes. So this is not good. Yeah, so this is not necessary. So let's go to this guy. Yeah, go to attack this guy. And the answer, which I postponed, is so this birational of Inose 2. And for this Inose Picard number 8, so this is very general. And Picard number 18. And this is finite. This is the main result of this section. And proof is almost similar to this part. Yes. We find a certain set of -2 divisors, Q effective -2 divisors, and and the region of this type is movable cone. Yeah, that's a strategy. And what? So of course, let me denote this X, and so pick X. As I write many times, this is pick Inose plus Z delta with delta square is -2. We get a new class delta with square -2 with divisibility 2. And this Inose surface has Picard on this U plus E8 plus E8 plus -2. Or you can say this is A1. Yes. And fortunately, this lattice is also reflective. Reflective means -2 reflective. Means group generated by -2 reflections has a finite index in orthogonal group. And the diagram is extension of Paya diagram. So Paya diagram. And how it extends. So this one has is in U plus E8 plus E8. And we extend this lattice by adding new -2 element. And okay. And we get 2 -2 divisors. No, 2 -2. Well, firstly, -2 class of divisibility 1, and I forgot what, and divisibility, some are divisibility 2. And what? So the easiest one is F. I'm sorry, I used the bad notation. Let me see. So, oh yeah, here I the remain D. So this is D. So D minus delta. This is 1. So D square is 0. So this is elliptic vibration. And second one is you can find another elliptic fibrillation by choosing this way. Then this one has how many vertices? So this has 17 vertices. Am I correct? 16? 17, yeah. Yeah. So the 16 to the, yes, thank you. 16 is correct. Yes. Yes. And let's denote this. So with coefficient 1, 1, 2, 2, 2, 2, 2, 2, 1, 1. Then this maybe let's denote F. Then F minus delta is also minus 2 plus. Okay. And by, yeah. So by adding these elements, we have a circle. So this one is original pi diagram. But this new minus 2 divisor has intersection number with 1 with these two extremal ones. So this chain is closed and becomes a circle by adding the, no, F minus delta. And how becomes this one? Oh, I'm sorry. Sorry. The pi diagram is one. Yeah, pi diagram. So this is pi diagram. Sorry. Yes. And the new this minus 2, new minus 2 is attached to here. Because this is E8 Tudor fibrillation and this is section. So D minus delta has intersection number with this section. And the delta is perpendicular to the or peak innocent. So this is, so you can see the diagram has symmetry of S3. This has only symmetry of S2, but symmetry get larger. Okay. And fat. And so this is divisibility 1. And also we find 3 minus 2 classes of divisibility 2. And of course, 1 is delta, original delta. And another is, and where is delta? Delta is almost disjoint to all the classes. But if this one has delta, this one has delta, so delta itself is here. And intersection has number is 2, so I draw 2 lines. This is not the usual convention, but let me keep this notation. And by symmetry of S3, there's here you also have, and here you also. And the such class is explicitly given by 3H minus, no, 2H minus 3 delta, and 2H prime minus 3 delta, where AH is the inner-set polarization. So pullback of hyperplane section of this one. And H prime is just H moved by S2 symmetry. Then you get 2H minus 3 delta to 2H minus 3 delta. And I think this diagram was missed by original paper of Nikurin and found by Kondo-san correctly. And okay. And so how many? 18 plus 2. So these 24 minus 2 divisors satisfy similar. I'm sorry, still not divisor, I'm sorry, minus 2 classes. So similar property to 19 C1 C9. So namely, if alpha has a self-intersection number with these classes, then implies alpha square non-negative. So the crucial property is this one. Yes.
All minus 2 plus?
All minus 2, all minus 2. So for example, 2H minus 3 delta square is 4 times 4 minus 9 times 2 is minus 2.
And these are all possible.
No. This is some kind of generator. Yeah, generator. All minus 2 classes are obtained by repeating deflections to these. I'm sorry. I say yeah. So this is 24 minus 2 classes. And so the problem is so we have to show these all 24 classes are all Q effective. And they have a geometric meaning. For example, this one or this one are coming from elliptic fibrillation. So if you have elliptic fibrillation, and if you consider it's Hilbert square, then you can consider the pair of points such that fx equal fy. Then this, but not x equal not y. X and y are different, but go to same point of P1. So this is yeah. Then this gives minus 2, or maybe take closure. Then this is minus 2 divisor. And so this is effective. And this is also effective. And the problem remains for these new classes of divisibility 2, yes. And of course, this original one is Q effective. Yeah, Q effective. As I already explained, so the delta twice of delta contains diagonal exceptional divisor of S2 going to S. And I have to show similar factor holds for this one. So this is divisibility 2. This is also divisibility 2. And why? So let me denote this delta delta prime, and this is delta double prime. So the crucial point is to show delta prime and delta 2 prime is also a Q effective. And to show this part, I use Inose polarization, Inose realization. So SAB is minimal resolution of this quadratic, and S2AB has Beauview involution. Namely, so if you have 2 points, then you get 2 points here, A bar, B bar, and consider take line joining A bar and B bar. Then when A and B are general, then this LAB intersect with S bar AB at 4 points. So A, B, and C, D. And consider the map to itself by sending AB to remaining residual CD. This is called Beauview involution. And this Beauview involution, this Beauview send class delta to delta prime and delta double prime. So this is Q. So the fundamental domain was surrounded by walls, -2 walls, which are all Q effective. So movable cone of S2 is something like data. No, negative for all these 24 -2 divisors. And the rest is the same to the Inose case. Finally. I still have 20 minutes or 25 minutes. So yes. Mm-hmm. I think S3 is so that the symmetry of, yeah, that's all. Yeah, that's all. And S3 is generated by two Bovio involutions.
And for the surface itself, what is the
I think it's the only C2. Yeah, C2, only C2. Just, yeah, or S2, yes, as you see. Yeah.
they can't
No. Yeah, you are correct. Correct. SN+1. But this is contained, yeah, but of course this is guess, I think, yeah. Let me see. No, maybe no, not so easy. I cannot answer now, sorry. But for n bigger than 3, I think this is infinite. Normal finite. Yeah, normal finite. So this for the Hilbert square is very special, yes. If you go higher dimensional, it's difficult. Okay, so next one is section 4. It's as I wrote in my abstract. Let's go to Bimberg. Yeah, I think, yeah, still, so SN+1 is still a good approximation. And yeah, in some sense it's correct, but let me, yeah, I forget. Yeah. Yeah, it's a good approximation, yes. Good approximation. So fat. I already erased, but Bimberg surface. This is K3 surface. We only have two. This appeared in his paper called Two Most Algebraic K3 surfaces. And this is just the exception. In the proof which I introduced just, yeah, of Shioda Inose 77 paper. So this has a elliptic K3 with 2E8 fiber, but in this special cases, they have another fiber. So for S3, this has A2 and 2E8 plus 2A1. And this is equivalent to say that transcendental lattice which is perpendicular, also a complement of Picard lattice in the H2 is in the first case A2, a positive definite A2, and in the second case positive definite 2A1. So this has discriminant 3, and this is index 3, and this is index 4. And the main theorem of Bimberg in 1983. I think this is a seminal paper in the study of explicit full infinite automorphism group. And he showed that automorphism group of S3 is free product of 12 copies of involutions. Group of order 2. And similarly, automorphism S4 is free product of 5 copies of five involutions.
When you write
Yeah.
this book, you cannot find it for the.
Yeah. This is means there is homomorphism with finite kernel and but let me write more explicitly by my reason, or more precisely. More precisely, so let me first describe S4. S4 is a double cover of blow up of 5 points of P2. So this is a quintic del Peso surface, double quintic del Peso surface. And the branch is a union of all the lines, 10 lines minus k lines. Yes. And so the automorphism group firstly contains C2, which is a covering involution, and the quotient is some blow up of this quintic del Peso surface, and this has semi-direct product of this C2 star 5 by automorphism group of this DP5. Thank you. Yeah, sorry. 4. Yes, thank you. Yes.
It's single or like it's lines intersect.
Yeah, so 10 lines intersect. Yeah. Sorry, thanks. Yeah, that's better. Yes, yeah, thank you. Yes. This has 15 nodes. Yes. And take minimal resolution. Yes. And I think S2 was studied by Donten, Berry, and Wisniewski. Yes. That's very special. But today, I'm interested in the other case. So other case is similar. So in this case, we take triple cyclic cover. And so tau cube is x square minus x, y square minus y. So branch is this one. So this has 9 cusps. And take minimal resolution. Okay. Then automorphism group of S3 contains C3, which is a covering group of this part. And the quotient is this one. And we have a semi-direct product of this free product by finite group S3 cross S3. It takes, so this S3 is interchanging of this three, and this vertically, and this another one is horizontally, and C2 is interchanging this P1 crop of two factors. Okay. So my target, the next target is what is birational automorphism group of this Hilbert square of Weinberg surface of discriminant 3, minimal discriminant. Maximal pickup number and minimal discriminant. And let me let me explain my first surprise. This is a little bit small, but still surprise. So this surface, Weinberg surface has a finite symmetry of this one, but this symmetry is extended to symmetry group of order 6. So S6 is contained in this guy. And the reason is this. So S3 bar, so I denoted it triple cover of P1 cross P1, but this is intersection of quadric and cubic P4. So this is a cone over P1 cross P1. And this is this equation. And as I explained yesterday, in such situation, you can consider nodal cubic fourfold. I'm sorry, nodal is good, not good, singular. Inside of P5 by adding new variable x naught, new variable, and this quadratic equation and cubic equation is 0. It's P5. Then, as I explained, not so fully explained, but S3 Hilbert square of this guy or its resolution is birational to this one. Panel scheme of lines in cubic fourfold. And the symmetry of S6 is comes from symmetry of this cubic fourfold. So because this cubic fourfold has 10 cusps, I mean quadratic extension of usual A2 singularity, or what is the name? Classical singularity, or yeah, some A2 singularity. because 9 cusps comes from that of S3. And 1 is this 1, 0, 0, 0, 0, 0.
Small number of cusps.
Yes, yes, that's what I want to say. Yeah, I'm going to say yes. So, as you already heard, this is a claim. So, observation is so 10 cuspidal cubic fourfold is unique. And what is that? I explained using what? Using beanbag surface, but the honest or simple, much simpler way to get to this one is Segre cubic, and this is 4. Segre cubic 4. This is triple covering of triple cyclic covering of what? Of T4 with branch. Classical Segre. 3. So it is by equation, it is written by extending P4 to P5, and this part is sigma Ti is 0, and sigma Ti cube is 0. And this has obviously S6 symmetry. And this is QED. Or QED of this surprise. And next surprise is much bigger. Yeah. Huh? I don't know. I can write, but I never. Yeah, not so natural. Yeah. And surprise 2 is S7 is contained. And this case, this is contained in naturally in FV34. And this is, I'm sorry, this is in automorphism group of F34, and this is subgroup of birational group. Yeah, so. Yeah, as is remarked by Dan, yeah, it's, this is not I didn't write the equation action in the original model, not S2. But this surprise is contained in what? In birational automorphism. I don't think this is, it doesn't lie in automorphism group. I'm sorry. Yeah, auto. This is same as bill of S3. And I need some step to show this claim. Yes. So, no, not this. this one. So there exists 35 minus 2 divisors with whose dual graph whose dual, so then the 30, so arrangement or maybe configuration, configuration. Of 35 minus 2 whose dual graph has symmetry of this. So I first show it combinatorially. And this 35 is divided into two parts. So 20 and 15. And 20 comes from 10 cusps, or its resolution. And their configuration are 10A2. So this is 20 minus 2 divisors effective of FV3 coming from 10A2 of V3. But what's this 15? So 15 is corresponds to plane in P, plane P in V3 4, or plane in Segre cubic. So Segre cubic, sorry. So so for what are these 10 cusps? Yeah, where I wrote the equation. Oh yeah, this part. Yeah. So 10 singular points are indexed by yeah, this one, 1, 1, 1, minus 1, minus 1, minus 1, etc. And on the other hand, you have also 15 planes. So T1 plus T2 equal T3 plus T4 equal T5 plus T6 equal 0, etc. This is 15.
Can I ask for this?
Yes.
So it moves around the cubic, but divisors are on the panel. Right?
Yes, also. I forget, sorry. Let me. So, yeah. Yeah. I learned it in some paper of Yamagishi, but I forget to learn. Yeah, sorry for. And in this case, it's easy. So if you have PP, then consider all lines which has which meets the plane. Then this dp, this is in FV3 minus 3 divisors. Can I have 5 minutes? Sorry. So one cannot see immediately from this parameterization. So 20s are parameterized by this type of permutations inside symmetry group order 6. And 15s are parameterized by this type of permutations. But let's go to another world by outer automorphisms. Change. Then this is stable. This is the same conjurous glass. And this goes to this one, just transposition. I'm sorry. I'm sorry. I'm sorry. So 10 singular points and 20 divisors. I'm sorry. So to 20 is not this one. But, I'm sorry. I'm a little bit confusing. Yeah, so sorry. So this is 10 and this is maybe it's interchanged. Sorry. Okay. Yeah. Sorry. A little bit. Yeah. So these totals are I forgot. So 10 or 20. I forgot. Yeah. Anyhow. Operate non-trivial outer automorphism of S6. Then this changes into this. This is makes us our task very easy. So our 35 minus 2 divisors are indexed by union of three sub 3 set of this one and this joint union of two sub 2 set of so parameterized by subsets of cardinality 3 and 2 in this one. But introduce new or dummy alphabet 7. Then this is just this way. So this is nothing but the set of cardinality 3 in the fixed. So all minus 2 divisors are indexed by dijk. ijk are subset of this one. And we have following simple intersection property. Let me use I, J. And there are only 3 possibilities. So this is -2, when I equal J. And when this is disjoint, then this is 1. And this is 0 otherwise. And obviously, S7 symmetry. And what we have to do is do this geometrize. And the answer is use Lagrangian fibration by Lagrangian. So we have to extend the symmetry from S6 to S7. So we need an element of order 7, for example, this one. And we find a heptagon. So inside. Okay, so 1, 2, 3. And then next one is 5, 6. 1, oh, no, 7, 1, 2. This one is 3, 4, 5. So this is the sigma cube gives heptagon. And this heptagon has this one and this one. And so you get Lagrangian fibration with A6 tilde 3 fibration. And this model Bay group has the 7 torsion, and you get order of 7 birational automorphism group order 7, and you get the S7. And my theorem, let me write my theorem. So my theorem is so birational group of Hilbert square of Wingberg surface is something semi-direct product, and the something is infinite group, and infinite group is generated by 84 plus involutions. Yes, generated, but there's a non-trivial relation, so this is not a free product. But I can construct involution so that they generate birational automorphism group together with this symmetry of S7. Yes. Thank you for your attention. I think.
Thank you very much. So are there any questions? So if we look at Hilbert square of S4, do we also have some surprise?
Oh, thank you. Yes. As I already mentioned, that was already studied by where I wrote. I already erased. I think Dontenberry and Wisniewski, they already found symmetry. So S42 has semi-direct product of semi-direct product of elementary abelian group by S5. So this S5 is the automorphism group of quintic delta. But this part is added. Yes. They showed this by using the EPW model. They quite explicitly wrote down the equation of sextic of in P5 of this, and this is the double cover, and the equation has this group of symmetry. Yes.
So are there more questions?
So do you think it could be true that birational automorphisms of hyperkählers are always generated by elements of finite order, like in this example?
No, not necessarily. That's too much.
But can one disprove this? Like, do you have an example when it's not
Yeah, I
generated?
think sometimes birational automorphism is Z, infinite cyclic.
Okay.
Yeah. Or Ah, Conway group. I see, I see. Okay, Conway group is very far from from this. Not very far, but far. So it's next section, which I omit. OG10. OG10 and super singular. And OG. Oh, I'm sorry. Conway 3. And yes. And I explained segregate cubic waffles. And from this one, you can construct OG10, but a very special one, OG segregate 10, which is has Lagrangian fibrillation over P5 star. This is a dual of ambient. And this is a union of intermediate Jacobian of hyperplane section. Yeah. And this one has symmetry. I think this is expectation. I expect. Symmetry has U3, 4. This is a symmetry of Helmer quadratic. X4, Y4 plus Z4 plus D4 equals 0. But consider over F9 in characteristic P, characteristic 3. Yeah. But further, so this one is already obtained by Lazar, constructed by Lazar, Saka, Guazan. In the very general case, cubical, and also by Saka, when this is smooth. And in private communication, I heard that Lazar, by Lazar, this is also possible for rational double point case. Yes, so it's okay. But consider mod 3 reduction of this very special OG10, so OG segregate 10. Then my expectation, this has action of Conway group of 3. So this is my guess, but it's a little bit far from this talk, because I started from K3 surface of Picard number 1, Picard number 20, maximal one. And I gained 1 Picard number by considering this Hilbert square. And rho equal 22 is obtained by going to OG factor, OG segregate. Segregate 10, yes. And there's another way going to Picard number 20 is mod 3 reduction. Then this becomes a Feldman quadratic. And the final one is just amalgam of this one. And this is OG segregate 10 mod 3. And this has a Picard number 24. And this may, I conjecturally this may have action of Conway. So for K3 level, automorphism group is inside M12, 21 or M22. Yeah. No, I'm 23, 23 or 24. But when considering higher dimensional analog, higher dimensional generation, or super singular something, you get two more Picard number by each steps, and combining them, the biggest one is this one. But this is the limitage of my technology, and I cannot go to monster. This one is very far.
So maybe one last question.
So what first words? Is it? I think computation is. I don't like to compute, but it's easy to distinguish. Yeah, to compute negative class. I think in the case in this S2 case. In this S2 case, only -10 class. If this appears, then this obstruct. This is obstruction for birational automorphism becomes biregular. So just you have to solve a Perry equation or something like that. Yeah, that's.
So let's thank Professor Mukai again for his wonderful lecture set. Okay, so in the room 504 is the place to sign up for per diem. And in order to avoid that many people visit at the same time, so please refer to the schedule on the wall and also on the door. Yeah, and as yesterday, lunch boxes are outside.